Welcome to another episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
Again to another episode of our show, bringing you another fascinating guest today involved in creating a better tomorrow for all humanity. Today we have the honor of being joined by Dr. Tony Donne, who is Chief Executive Officer and Program Manager of the EUROfusion Research Consortium, which is a European consortium of 30 national fusion research institutes across 26 EU countries, including Switzerland and the Ukraine, where he coordinates a network of over 4,000 scientists and engineers, and he's held this position since 2014, when the organization was established to succeed the European Fusion Development Agreement. Dr. Donne trained as a physicist, initially obtaining his master's in experimental physics at Utrecht University. Then he did his Ph.D. at the Free University of Amsterdam for work in the field of nuclear physics, and moved immediately into fusion research right afterwards, and has devoted a significant part of his career to the design and use of plasma diagnostics and large range of fusion devices. Prior to EUROfusion, Dr. Donne was the head of Fusion Physics Division at the Dutch Institute for Fundamental Energy Research, or DIFR, and responsible for the coordination of nuclear fusion research in the Netherlands, where he coordinated the Dutch fusion research as Director of Fusion Science and Acting Director. He has served additionally as professor in diagnostics and heating of fusion plasmas at Eindhoven University of Technology, as director of the Dutch-Russian Center of Excellence on Fusion Physics and Technology, as well as a program manager of the International Thermonuclear Experimental Reactor, or ITER, Netherlands Consortium, and chair of the coordination committee of the International Tokamak Physics Activity under the ITER project. Extensively published, hundreds of peer-reviewed journals, hundreds of conference proceedings. We're honored to have him with us today. Dr. Tony Donne, thank you so much for taking the time to come on the show.
Well, thank you very much, Ira. I realize now that I should stop adding things to my CV, because the introduction almost becomes longer than the actual interview. But thanks for introducing me and in the show.
Yeah, no, it's great having you. I really, enjoyed going through your bio, and I also spent a little time prior to the show, sort of going through the publication database, and I actually went all the way back to the beginning, and I bumped in the IAEA database to your dissertation, which was entitled "Transverse Excitations of Fluorine-19," which here's the dissertation that, as I said in the bio, started all this off. Talk a little bit about that, if you would. Take us back to those early days. What got you initially excited in sort of this fascinating domain of fusion? And then also, just as a second part of that question, talk for a couple of minutes about the drawing at the beginning of your dissertation, because I also found that quite interesting, where you sketched out the spectrometer room and there was fish tank and mice running on the floor and other stuff happening. What was going on back then? If you could say a couple words about that as well.
Oh yeah, well, very great. Well, actually, this is the first time I get in an interview a question to go back to that time. Well, actually, I came into my PhD. Well, I would say by coincidence. When I did my master's at Utrecht University, I was doing solid state physics. I was doing nuclear physics, and then I got a few options to do a PhD, and the one in Amsterdam really excited me a lot. where I was responsible for building up a scattering facility, an electron beam scattering facility, and to do first experiments with that. And it was an exciting time, so I liked using my hands. So it was very interesting building or rebuilding the facility, because it was a spectrometer which has been used before. Yeah, I did that with a small team, and ultimately when it was completed and the accelerator came up and running, we were doing first experiments which were very exciting, and I've been working like day and night there to really secure the data for my thesis. And I liked drawing quite a lot, so I've been drawing the scattering facility, and then I wanted to add some little jokes. So indeed, I converted one of the magnets in an aquarium, and I had a little mouse, which indeed, so now and then we had mice in the control room, especially when you're working at night. Right. I was usually with one of the colleague. We always had to be with two persons. And then sometimes you were just sitting silent because the data were taken and you were not moving. And I remember on one occasion a mouse was sitting on my shoe, and so yeah, but it's just a little joke. So
gotcha. No, that was great.
Yeah, actually, then after my PhD, I had two postdoc offers, both to come to the United States. But at that time, my wife, she had a permanent job at Amsterdam, the Free University in Amsterdam, and I didn't want to, let's say, go for 2 years totally alone. I also am of the opinion that women and men should have equal rights. So I then, since she was the first, I tried to adapt my career, which meant that I switched to a slightly different field. And I went into plasma physics, where they were looking for someone with a nuclear experience, a nuclear background. And I was lucky that in the new laboratory, I was, let's say, efficient relatively quickly. So already within a year, they offered me a permanent job. And interestingly, I entered the field roughly at a time when Ronald Reagan and Mikhail Gorbachev agreed on the ITER project, which was back in 1985. Mm-hmm. So it was very interesting to enter in a very exciting period, and ever since then I like the field very much, and certainly working with diagnostic, you work with many different corners of the physics basis. So you work with microwave diagnostic, with laser diagnostic, spectroscopy, particle beams. So I've been doing everything, and I found that very interesting. And also being involved in data taking and doing some exciting work there. So yeah, so then I once I was in, I stayed in the field forever. I'm still there.
Absolutely outstanding. No, thank you for that great intro. I really appreciate the background stories to a lot of our guests, and I do appreciate that one. Tony, so in order to sort of lay the groundwork for a lot of the audience that may be less familiar with some of this science, clearly, when we talk about fusion, here we have I guess in current lingo is the killer app of energy production, in terms of here we're clearly harnessing the dynamics that occur in the very center of our sun, and have been powering it for millions of years, and will continue to power it for millions into the future. And really there's two, as far as I see it, and I come from a life sciences background, sort of two basins of technologies that have been developed over the decades to make this happen. On one hand, we have the materials, the energetic materials. In this particular case, these novel isotopes of hydrogen. In some cases, you're slamming other particles together. We'll get into that in a little bit. Here, primarily deuterium and tritium isotopes of hydrogen, fusing them together to create helium and releasing a tremendous amount of energy and heat in the process. On the other hand, we have the tokamak technology set. So tokamak standing for the toroidal chamber of magnetic coils, this concept that was originally developed, I think, back in the 1950s, that in order to harness this energy and keep it somewhere stable, you need these powerful magnets to control it. Introduce us a little bit to both the raw materials that go into this process and the unique technologies required to control this amazing energy source.
Yeah, so actually it boils down to first look what happens in the sun. So in the sun, you merge hydrogen nuclei, simply simple protons. You merge in a kind of stepwise process to helium, and you create a lot of energy. And this happens at a temperature of 15 million degrees. Now, to do that on Earth, we need a slightly higher temperature because the sun, you have enormous gravitational forces. Which means the particles are already relatively close to each other. And at these very high temperatures, you only have atomic nuclei and loose electrons, but there's all the particles are charged. Yeah. And so when you want to charge two light particles, which are positively charged, you need a lot of energy such that when they collide, they have enough energy to overcome their repulsion. And this means on Earth we need a temperature of 150 million degrees. So it's a little bit higher. And then if you look at what are the easiest reactions on Earth, by far the easiest reaction is the one between deuterium and tritium. Deuterium and tritium are both forms of hydrogen. Maybe for the listeners, deuterium is, well, you can call it heavy water. So normally hydrogen, the atomic nucleus has a proton. Deuterium has a proton and a neutron. Mm-hmm. And there's double the weight of normal hydrogen, but chemically it's identical to normal hydrogen. And deuterium occurs in natural water. So it's very easy to extract that, and we can use that. Tritium is also a form of hydrogen, but it has two neutrons and a proton in the atomic nucleus. So you could call tritium a super heavy hydrogen. Again, chemically identical to normal hydrogen. But tritium is not stable. It's a beta emitter means that typically within a lifetime of 12.5 years, it converts to 3 helium, and thereby it becomes stable. And all the tritium we ever had on Earth, let's say natural, is basically gone, because with a lifetime of 12.5 years, nothing is left. But you can produce tritium. At the moment, it's a byproduct of certain types of nuclear reactors. Mm-hmm. So you can do type of reactors. And at the moment, we had the commercial supply of tritium is in the order of 25 kilogram worldwide, mainly in Canada, Korea, and Romania. And these are the materials. And but it's not enough. So if we think about an enormous fleet of fusion reactors, we need typically, I would say, for a big reactor powering a city of 5 million people, you need in the order of 200 kilogram, 300 kilogram of tritium per year. Yeah. And of course, we don't have that available, but we can make it ourselves from lithium. So you could say the raw materials we put in the fusion reactor are deuterium from water, which we extract from water, and lithium, which we could basically extract from used car batteries. Because also there we only need for a city of 5 million people in the order of a few hundred kilogram, which is almost, let's say, one car battery. Although we use enriched lithium-6, which means we need a little more car batteries, or we need to. So that's the idea. Now, getting something 150 million degrees is not too difficult. We do that every day in the laboratory. As said, at these very high temperatures, all the particles are charged, and charged particles you can confine with a magnetic field. And there's a Russian invention called tokamak. You already mentioned that, Ira. And tokamak is actually a kind of donut-shaped magnetic field. So it's really like a donut or car tire. And the magnetic fields are around the hot plasma, and they confine the field. So we have coils in many different directions because we need to keep it stable. We need to prevent the very hot plasma touching the walls, but we are able to do that. And so at the moment, the state of the art is that at the one hand, we have been conducting fusion experiments. So in Europe, in the Joint European Torus earlier this year, we reported that we generated 59 megajoule from fusion in a 5-second pulse. And the 5-second is limited by the fact that this device has copper coils. And we can only operate the copper coils at the highest performance for 5 seconds, because then they get too hot and we need to wait some time until they're cooled. 59 megajoule is, let's say, about the energy you need to bring 60 kettles of water to cook. So a kettle is, well, even in Wikipedia, it's not very precise what a kettle is, but it's about 1.6 liter. So 59 megajoules is about 100 liters of water, and we brought it to boil with only 170 microgram of fusion fuel. So it's less than a grain of sand, and we get the water boiling. If you want to do it with coal, you would need 4 kilograms of lignite coal. So fusion is enormously power dense. So we now have these hot plasmas. We can create the conditions where fusion occurs. We have also already, especially in China, but also Europe, we have machines which have superconducting coils to generate a magnetic field. And these machines can basically generate a magnetic field continuously. And so, especially in China, Korea, they have already achieved pulses of 1,000 seconds. So you can stretch the pulse much longer, but these machines are not working at the same performance as we have in Europe. And now the idea is that we are working with, I would say, almost 2/3 of the world population is behind the ITER project. So ITER is the Latin word for the way, and it's, I think at this moment, the largest international project worldwide. It's even a little larger than ISS. If you integrate it over time, ISS will be a bigger collaboration. But but this brings together the United States, Europe, Russian Federation, which despite the war are still involved. Japan, South Korea, China, and India. We are working now on establishing a machine which is going to deliver 10 times more fusion power than the power we put into the hot plasma. It will not generate electricity yet, but it will at least show that well, fusion is feasible. It will work under the same conditions as we have in a reactor. And in parallel, let's say many countries are now working on the design of demonstration reactors, which should deliver electricity to the grid by the, well, somewhere 2040s, 2050s. I personally, I think it's closer to the 2050s, because at the moment there's also many private companies in the field, and they all come with promises. We have a fusion reactor working in the next 5 or 10 years. Right. But these are very often, let's say, horizons which are important for investors. If you go to an investor and say, well, I have a giant idea for a fusion reactor and it worked by 2050, then they say, well, come back by 2040, and then we might pour money in it. Right. So you come up with, let's say, promises you never can keep. And but it's nice to have these companies around as well.
Excellent. So before we dive a little more into what's happening in France with the current device, or the one that's going to come online next decade, talk a little bit about EUROfusion in general. I mean, it evolved from a previous organization back in 2014, funded sort of a little over €1 billion or so from the European Atomic Energy Community, as well as from member states. Talk a little bit about the structure, a little bit about how you go about working with the various countries, the grant making system. Introduce us a little to EUROfusion, if you would.
Oh, that's interesting. Well, actually, I should say there that before 2010, so about 10 years ago, every country had its own individual fusion program in Europe, and we had only one common machine, that was the Joint European Torus,
right,
where we all agreed to work on. But then every country had its own program, and the European Commission was funding up to 20% of that fusion program, up to a certain ceiling. But since every laboratory was independent, what happened is that there's a lot of duplication, because everyone wants to jump on the more sexy work, which gives you nice publications, nice breakthroughs. And there's also work which is very important and no one is doing, because, you know, it's not so let's say rewarding in sense that you don't have nice publications, etc. So it was then that the European Commission said, well, sorry guys, you need to get your act together. You need to develop a roadmap. We want to see a clear roadmap to see where Europe is going. And in contrast to most of the countries in the world, if they present a roadmap, is one slide where you can see a timeline. But the European roadmap is really a lengthy document in which we did a very thorough gap analysis to see where are we now, what is our knowledge status, what do we need to do to get to a working fusion reactor, and we sketched the time path. And then once we had the roadmap, we set up EUROfusion. And so the European Commission has outsourced the coordination of the fusion program to EUROfusion, and we are a consortium of 31 national research institutes in 29 European countries. We're doing that. So we all agreed now on the priorities. And the good thing is that, so centrally, we decide where the money is spent, of course, on the highest priority research. But the Commission is paying typically half of the money, so the other half is national matching. What you automatically see happening is, because we put the money in certain baskets in the laboratories, they are going to put also the national money in the same basket. So slowly this has led to a change and a much greater coherency in the European program. What interesting, originally many of the lab directors, they were very worried, because they thought, well, this is a very competitive scheme, because we organize everything by calls. So whenever I want to distribute money, I make a call Europe-wide. The lab directors can react, and we choose the ones which are best. And of course, there was a worry that some labs might not get any money anymore. And then in practice, it turns out that everyone is still involved. And we're using the strong points of all the different laboratories, even some very small countries, Estonia, Latvia, Slovakia, Malta, which have a fusion effort, which is basically maybe 5-10 people. They are still involved because they are really working on, let's say, using their main competences, and they're not trying to cover the full field. So in principle, EUROfusion works relatively well. Of course, there's always things you can improve and do better. We involve roughly 4,000 researchers, scientists, engineers all over Europe. And we just closed our first framework period, the first 7 years, and we achieved more or less all the deliverables we promised. Of course, it's research, so it's very difficult to already at the onset, you don't know what is coming out of the research, but at least you say, well, we are going to study this and this, and at the end of this period, we have a report on this. And in many elements, we're making progress. What we also started, and that's more recently with, is to use a scientific maturation plan, which is a completely new concept. People know about the technology readiness level, and a technology maturation plan, which we had already in our demo activity. So we are working on the design of demo. And in many areas, the technology readiness level is very low. It's maybe 2 or 3 on a scale of 10. And you want to bring that to a higher level. So at the end that you're competent, that you can manufacture components. So it's not enough that you know in a laboratory how to do it, but you really need to work with industry to make this. So we had a technology maturation plan, but we're doing now the same also in the field of science, where, let's say, for all these scientific points which we think need to resolve before we get to a working reactor, what is the status now? Do we have a basic understanding? Do we understand everything? Is just a kind of emerging idea which we still have to find out? And so over the years, we're also following the progress now. We can see that we're making progress. So in this sense, it works quite well. EUROfusion works over the full scope of fusion. So at the one hand, we're doing, but we are a research organization. So we are doing research on contemporary experiments, which are tokamaks, other confinement devices, linear devices where we test materials. We are doing engineering for a neutron source to ultimately test the fusion materials. What we are not doing is building big devices. So ITER is built by another European agency, Fusion for Energy, which is our domestic agency for ITER, and they, together with the domestic agencies in the other partner countries, are building. So they are really there for arranging the procurement. But we are now doing the engineering design of the demonstration reactor. But once it goes into a more detailed engineering design, where you have to work with industry and start getting bigger contracts, then the idea is this will go over into the Fusion for Energy organization. But we are really focusing more on the research part.
Excellent. Excellent. And, you mentioned the roadmap. And so, we have sometime 2040, 2050, where we have full realization of fusion electricity around the world. The France project, which you mentioned, about 10 times coming out what we're putting into it around 2077, 2028, and I think I watched a presentation of yours that this facility is something around 80% complete or so forth. I'm here on the East Coast of the United States, and there are some traditional fission nuclear power facilities around this area. Have somewhat of an idea of sort of the scale. If one was just to go to the Southern France project today, what is the scale of something like this experimental reactor like? I mean, just for the audience listening and watching, just to put it in perspective to other, we talked about coal and natural gas facilities, of which there's plenty around here as well. What is the scale? I mean, what does this look like? And compared to a football stadium or a Starbucks, put it in some reference frame.
Yeah, it's definitely larger than a football stadium.
Okay.
I think you best can compare it with a let's say a big fission plant or a big fossil fuel plant. So the footprint is typically, I think the site is something like, well, this is a wild estimate, but it's order, I think 700-800 meters by 600 meters, something like that.
Okay.
That order.
Okay.
So it's not larger than other big power plants. It's definitely not the area you need for windmills or for solar plants, where you need much larger land coverage.
Sure. What, Tony, what does the term, because it came up in your bio a bit, and in a lot of the materials that you've published over the years, what does diagnostics mean in the nuclear fusion domain? We talk a lot about diagnostics, of course, on the show in terms of infectious diseases and things of that nature. What does diagnostics encompass in terms of nuclear fusion?
It's diagnostics. It's a term for all the measurement equipment, all the sensors you have around a fusion reactor, and of course, you want to have, let's say, diagnostic equipment for a number of purposes. One is for machine protection. You need to, let's say, be sure that you are not doing anything which can harm the machine. You need to have diagnostics for control, because you need to, well, control whether the plasma is nicely contained by the magnetic field, whether it's not hitting any material surfaces. You want to measure the density, you want to measure the temperature, you want to measure the plasma composition, because there always could be impurities coming in here. If some energetic particles from the hot plasma hit a wall, then wall particles, they could come in the plasma, and if it's too many, then the plasma is diluted. You cannot operate it in a good way. And well, of course, you have also diagnostics for, let's say, the scientific understanding, because we're still in the experimental phase. And ITER will have in the order of 70 individual diagnostic systems with in total thousands of measurement channels. And that could be simple magnetic probes, which is just a coil which measures when the magnetic field is changing, gives a little current, and you measure that. It could be a laser diagnostic where for instance, we measure the temperature by injecting a laser beam, and we looked at the scattered radiation. And the hotter the plasma is, the wider the spectral distribution of the scattered light. And from that, we measure the temperature. And from the number of scattered particles, we get the density. We can use microwave diagnostics. So we send in microwaves. We look at their either reflection, scattering, absorption, gives information. We can look at the radiation which we get for free. So the plasma radiates, X-rays, visible light, ultraviolet light, gives us also information on the composition, on the temperature. We can shoot in neutral particles, so beam particles from an atomic beam, which we neutralize, otherwise we cannot get into the plasma. So you cannot shoot in ions because they are immediately deflected by the magnetic field. And we can look in how they interact with the plasma. So there's many different of these systems, which are important for studying. We use also, well, you could say the term diagnostics is mainly coming from the medical world. And we also use techniques which some techniques are quite similar to what is used in hospital. Like we use tomography. And tomography, we have a different, there's a difference between, let's say, the medical world and us. In the medical world, you have a patient who you can basically put on a bed for like 20 minutes, and then you have an X-ray tomography system which is going around and spinning around, doing a lot of measurements. Maybe that's also why they call the guy patient or the woman patient. Because it really takes time. In the plasma, the processes take place on millisecond level. And so we don't have a possibility to, let's say, take a lot of time. So we use many cameras around the plasma to look at the same time, and then reconstruct what is happening locally. And these systems are getting better and better. So we can get centimeter resolution in a device which has a volume of, ITER will have a volume of 800 cubic meters. So it will be really very detailed measurements.
Excellent. Tony, one of the guests I had on the show from the IAEA recently was Lydia Everard, head of safety over there, involved in inspecting the Chernobyls of the world and so forth, and obviously all the other facilities that are out there that do traditional fission work, and obviously we are all familiar with some of the issues that happen when we're dealing with some of those types of materials, the uraniums and the plutoniums and so forth. Safety in terms of nuclear fusion is a different thing. And you're not dealing with, we have this leak of XYZ over here, or the reaction is uncontrollable. You got to sort of You have a lot of benefits, obviously, and I heard you talk about some of those in a presentation you gave. Talk a little bit about that side of things, because we don't want to confuse the two. But obviously, when you're controlling 150 million degree reaction, you gotta, you know, I'm assuming there's, oops, if somebody doesn't turn on the magnetic field, you got a problem. Talk a little bit about some of the safety issues that not issues, but things that you got to keep in mind with regard to these novel
Yeah,
technologies.
good point. Well, safety is very important, and safety is really integrated in let's say all the work we're doing, especially in our design of demo. Safety is already involved in all even the very early designs of the machine. If you look at safety, so we have this very hot plasma, which is a huge volume, almost 1,000 cubic meter. But it is at a very low pressure. So typically the pressure is in the order of 1/10,000th of an atmosphere. So it's very dilute. And this means that at any moment in our reactor, we have only a few grams of fuel, which is in gaseous state or in plasma state. And we continuously need to puff in a low amount of this fuel to make sure that the reaction is ongoing. As soon as we stop doing that, the process stops. As soon as the magnetic field falls away, then the plasma at some point will hit the wall and it will cool immediately. Because it's so dilute, it will not really lead to major damage in the wall, but in a sense, you need to start all over again. In the worst case, always with the worst case scenario, there's a terrorist who puts a plane on your reactor building, and the reactor building should withstand that. But even if in that condition, let's say the plane comes on the roof and at the same time you have an earthquake, you get a tiny hole in your reactor. Then what happens is, since the machine itself, the core of the machine is under pressure, then cold air is going into the machine. And this will extinguish the reaction immediately. So it's not that there will be an explosion, it will be an implosion. And so the tritium will not automatically fly out. But again, the tritium is only minute amounts. There will be on the side maybe a few kilograms of tritium, but most is contained in bats, in storage bats, where we need to keep it available. So in that sense, we cannot have the equivalent of in fission reactors, a meltdown or let's say a chain reaction. So the reaction is well under control, and if anything happens, the reaction stops. Of course, one safety issue with tritium, tritium is very good in the sense it doesn't accumulate in your body. So even if you would get tritium in your body, it doesn't, let's say, accumulate in your liver or your mills. Tritium is a form of hydrogen, so it occurs in your body as a form of water. And you also sweat it out. You go to the toilet, and the typical biological half-life time of tritium, if you would have it in your body, is 10 days. Nevertheless, we should not underestimate, because tritium, since it occurs in the form of water in your body, it can get everywhere in your body, and it could lead to damage. So we shouldn't underestimate it. But the effects are different from, let's say, the long-lived elements like cesium, radium, thorium, whenever you get them in your system. Of course, one other issue with safety is that our reactor wall will become radioactive, and this is because the fusion reaction gives helium as an end product with a neutron. Okay. The neutron will not feel the magnetic field; it will go into the wall, and there it will convert this energy into heating up the wall. But it will also breed the tritium, which we need. But a side effect of the neutron is also that it will make the wall radioactive. And in a fusion reactor, we have the possibility to choose the materials of the wall in such a way that they lose their radioactivity very fast. And at the moment, we are working with designs where roughly after 100 years you can reuse the materials again because the radioactivity, the remaining radioactivity became low enough. So the idea is that you don't need to store large levels of long-lived waste for 10, 100,000 of years, but you store intermediate level waste for typically 100 years, and then you can reuse them. So that's basically the safety aspects.
Excellent. Excellent. Tony, as you're funding, these various research projects, one of the things that popped up when I was sort of doing my low-level deep dive into this is the interest in certain fields of moving to sort of fusion interactions with less neutron component or aneutronic fusion reactions. And some of the things listed here were the deuterium helium-3 fusion, and then something else called proton boron fusion, which I don't know how high on the list these are of some of these different types of fuels that you're looking at. I know helium-3 is something that's always mentioned, that there's a lot of it on the moon somewhere or whatever, but other interesting parts of the research program in terms of the inputs that you can talk about in terms of these fuels.
Well, it's very interesting. I think it's very good to have the research on deuterium-3 helium and also proton boron reactions. The reason why we are not pursuing this too much in EUROfusion is because at the one hand, the reaction probability of deuterium tritium is about a factor of 10 higher than for deuterium-3 helium and also proton boron. And the temperature at which the reaction takes place is also a factor of 10 lower. So for proton boron, you need to go to a temperature of 1.5 billion degrees.
Phew.
And also the reaction probability is lower. And deuterium-3 helium is not that bad, so you need to go to almost 1 billion degrees. And again, lower probability. Plus, you need to get the 3 helium from the moon, as there's not really a big supply on Earth. And so this is the reason why we, I'm coming originally from the Netherlands, where we have a lot of bicycles, and you start riding bicycle with 2 side wheels. You do it as easy as possible. But once you learn the trick, then you basically do it more difficult. And the rear people which want to challenge go in a 1-wheel bicycle in the end. Yeah. I see it also with fusion. You start with deuterium tritium because that's the easiest reaction to get going.
Gotcha.
And then in the meantime, in parallel, we do research to, basically get to a situation where we don't have this problem with the intermediate level waste, where the reaction is more or less completely nuclear free. It's still a nuclear reaction, but you don't have the radioactivity issue.
Sure. I appreciate you laying that out. And a very apt analogy as well. Tony, one other guest that we had from the IAEA last year was Dr. Najat Makhtar, head of science over there, who we didn't talk at all about energy in terms of fission, but she liked to talk about all the other stuff that we can potentially get out of that research in terms of, you mentioned obviously healthcare, but she introduced us to this Zodiac project in terms of nuclear energy is very good at killing viruses and other nasty bugs and so forth. Are there things that we get out of nuclear fusion that are not energy related, that are somewhat interesting, things that we might not know about in terms of when we have materials that get to 150 million degrees? Any interesting insights from material sciences, I don't know, healthcare, anything else beyond energy that you can tell us about?
There are many. Actually, I had last week a meeting with a company who originally got the patent for developing the superconducting cables for the magnetic coils for ITER.
Yep.
They worked here in Germany together with the Karlsruhe Institute for Technology, and this company used the patents now in medical resonance imaging equipment. And they are a world market leader with an annual turnover of more than 2 billion euro or dollar. It doesn't matter because they're about equal per
Right.
year. So this is a good one. From my own experience in the Netherlands, we worked with a company which was doing explosive forming of materials. So if you want to bring a pattern in a metal plate, you can do that typically with pressing methods called a hot pressing or cold pressing.
Mm-hmm.
But at some point, this technology doesn't work because if the pattern is too sharp, you get cracks in your materials, which is not good. So they use explosive forming. So you have a mold of concrete with a pattern on it. You put a plate on top, and then you put some TNT. You explode the TNT, and the plate is blown into the in the mold. And during this explosion, the material becomes super viscous, and due to that, you don't get any cracks. And we went to this company to see whether they could make parts of the vacuum vessel of 6 centimeters thick stainless steel. And we asked them, can you blow a plate of 5 by 7 meters into a certain shape with 0.1 millimeter precision? And they did some simulations, and then after that they said, well, we can do it, but only 2 by 2 meters because our swimming pool in which they do the explosions was not bigger. But they did it, and they really exceeded to blow this plate in a saddle shape with 0.1 millimeter precision. We took the company to several industrial exhibits, and as a result, they are now making the cockpit of the Airbus airplanes with this technique.
Yeah.
And the company originally was 5-6 people. They're now about 200 people. And so this is another one. Other examples are remote handling, because in the Joint European Torus, we have remote handling to do anything which is in the inside wall. Because we already work with tritium, and so after a tritium campaign, we cannot send people into the machine.
Sure.
So we do it with remote handling. And so these tools are now used in the International Space Station. They're used for medical surgery, surgery on distance, where for very specific surgery, the doctor doesn't need to travel to another, let's say, country or another hospital to do the surgery, but he can service, let's say, more hospitals from a central site. It's used in deep sea robots. Actually, technology is also used for the decommissioning now of the Fukushima plant. So there's many applications of what I would call fusion technology already in other fields.
Outstanding, really outstanding. So you mentioned just before an exhibit where you demonstrated some of these other tools. What else is coming up in terms of EUROfusion, and as we enter 2023? Are there other conferences you're going to be talking at, Tony? Any other types of exhibits where we may hear you talk, potentially meet you? Anything else hot for the new year that you might want to mention? Please take the floor.
Well, of course, there are many conferences. There is a continuous stream of conferences. I think one which I'm really looking forward to is the IAEA Fusion Energy Conference, which is in October next year, and that's the conference where we will, let's say, present most of the DT work we did in JET. So last year we did a campaign. We have been doing the analysis. We made the announcement of the world record fusion energy, but we really needed time to digest the data. So we have a large number of presentations. At the same time, we also publish a special issue of the journal Nuclear Fusion, which is completely devoted to our DT work. So this is really a very interesting event which is going to happen. Of course, there's a continuous stream of conferences where we also report on our work. But I would say the IAEA is one of the bigger ones where we really focus on, let's say, the more recent breakthroughs.
Excellent. Really excellent. Tony, it's a amazing journey you've been on. And I just really applaud what you've been doing, and that you continue to do it as you move down this roadmap, which is obviously going to impact all of us in major ways. Again, for everybody that's going to be listening to this particular episode of our show across the various podcast networks or watching on our YouTube channel, you've been listening to Dr. Tony Donne, Chief Executive Officer, Program Manager of the EUROfusion Research Consortium, moving forward the roadmap so that all humanity can realize effective, safe fusion energy in the future. Tony, again, I want to thank you for taking the time out of your schedule to come talk to us for a little while. Obviously, thank you for everything you're doing there at EUROfusion. And as we say on our show here, thanks for creating a better tomorrow for all of us via what you're doing. Very, very impressive work.
Thank you very much, Ira. It was a pleasure to speak with you, and I wish you success with your podcast.
Thank you.